In this video, we are going to prove algebraic identities associated with complex numbers, identities number 5 and 6. Okay, let's look at number 5. We're proving that the complex conjugate of the product of two complex numbers is equal to the product of the complex conjugate of the two numbers. Okay, so we have Z1, Z2, and we're taking the complex conjugate. All right, well, that's equal to x1 plus iy1. That's Z1 right there. Z2 is x2 plus iy2, and we're taking the complex conjugate of that. So what I'm going to do now, I'll keep going to the right, is simply FOIL out what's underneath the complex conjugate bar. That would be x1, x2. Outer would be plus I x1, y2. Inner would be plus I x2, y1. And then the last. What is the last? Well, we have an I times I, which is negative 1. And then y1, y2. So we have minus y1, y2. And then we have all of that with a complex conjugate bar. All right, let's see. Maybe I can just go straight down from here. All right, so underneath the complex conjugate bar, I'm going to put the real terms together, the ones that have no I. So x1, x2 minus y1, y2. And then put these two terms together since they both have an I, and I'm going to factor out the I. That will give us x1, y2 plus x2, y1. And then we have the complex conjugate bar. Well, now this is just a complex number written in standard form. Here's a real number, that's the real part, plus I times another real number, the imaginary part. Okay, so the complex conjugate, I'm going to remove the complex conjugate bar and turn this plus into a minus. So we get x1, x2 minus y1, y2 minus I times x1, y2 plus x2, y1. Let's distribute the negative I through here. And we'll get x1, x2 minus y1, y2 minus I, x1, y2 minus I, x2, y1. All right, now notice that this, I'm going to factor by grouping, but I'm going to group these two together because they both have an x1. And so it would be x1 times x2 minus I, y2. All right, now I'm going to group these two terms together, and this is where it gets a little bit tricky. I've done this before, and it's simple to verify what I am doing, but I'm going to do minus I, y1. I'm going to factor that out of both of them. So if I have minus I, y1, that leaves me with x2, and we're going to find out that the rest of it leaves me with minus I, y2. Now let's verify that. Let's distribute this through and make sure we get these two terms. Well, we know it works with the first one, negative I, x2, y1. That's this right here, negative I, x2, y1. Now when we multiply these two, a negative I times a negative I is positive I squared, which is negative 1. Negative 1 times y1, y2 is negative y1, y2. So these two lines are equivalent, and we continue with our factoring. Pull out this common factor, x2 minus I y2 times x1 minus I x, let's see, these two together, this would be x1 minus I y1. Sorry about that. x1, I'm factoring out, so yeah, minus I y1. All right, so what does that give us? That gives us, get rid of that parentheses. All right, so we've got x2 minus I y2 and we have got, sorry, this is not a, really messed that up. This is a product here. I was factoring incorrectly. I chose these two. These are the same factor, so I pulled it out. So it's going to be this times x1 minus I y1. Sorry about that. And now we've got x1 minus I y1. That's just the way it should have been written. And notice that we have z2 complex conjugate here. And here we have complex conjugate of z1. So that is, in fact, I'm going to switch the order. z1 complex conjugate times z2 complex conjugate. Again, I switched the order here, but that's fine because of commutative property for multiplication of complex numbers. Okay, now let's move on to number 6. Number 6 is much easier. We're proving that the complex conjugate of the complex conjugate of z is z. So, the complex conjugate of the complex conjugate of z is the complex conjugate of the complex conjugate of x plus iy. I'm going to put this in parentheses so it's make it obvious what I'm doing. If we ignore the top complex conjugate, we're taking the complex conjugate of x plus iy, and that'll give us x minus iy with one complex conjugate bar. And the complex conjugate of this is x plus iy, which is simply z. End of proof. Z complex conjugate is simply z.